So I left my document camera and my nice microphone at home, but we'll have to make do with this. I'm going to do it all via screenshot. I want to talk about the second derivative today. Second derivative, concavity, and acceleration are the main things I want to talk about. So let's think first about what the first derivative tells us. The first derivative tells us if the first derivative is positive, that means the function is increasing, and if the first derivative is negative, that means the function is decreasing. So if I can actually draw this. So if I know the first derivative is positive, then my function is going to be going up somehow. And if my first derivative is negative, my function is going to be going down. But remember that this is showing rate of change. So let's think about what this would mean for taking the derivative of the derivative. So if I'm starting with some function f, oops, I don't want that up there. I'm starting with some function f. I'm going to take the derivative. Derivative of f tells me whether f is going up or down. I'm going to take another derivative. Get the derivative of f, or f double prime. So this tells me whether the first derivative is increasing or decreasing. Okay, if f double prime is greater than 0, then f prime is increasing. If f double prime is less than 0, then f prime is decreasing. This is what we already know. This is what it means to be a derivative in some sense. If a derivative is positive, means the function is going up, the function it comes from is going up, and if a derivative is negative, the function it's coming from is going down. But I want to think about what this would mean in terms of what f itself looks like. If f double prime is positive, what does that mean about f? Well, looking here, if f double prime is positive, then its slope is increasing. So if it started with a negative slope, let's say, for example, let's say it started with a negative slope. F double prime doesn't tell us whether f prime is positive or negative. It just tells us f prime is increasing, so it's going to the right on the number line. F prime is getting bigger. So if f prime happened to be negative, then maybe f prime is like this, so it's going down. But we know that f prime is increasing, so this is some big negative slope. And as f prime is increasing, because the second derivative is positive, it's getting less negative. So we're getting less negative, and less negative, and less negative. And then maybe we have a 0 slope, and then but f double prime is still positive, then the slope is still increasing. And then we see this sort of behavior. This is what f would look like if f double prime were positive. And if the second derivative were negative, then we have the reverse. We have slopes that might be positive, becoming 0, and then negative, and then becoming steeper and steeper and steeper. So this would be a graph of f again, if f double prime were negative. Here it's f double prime positive. So what we get here is that the second derivative of f tells us something about the shape of f, but it doesn't tell us whether it's going up or going down. It tells us whether it has this U shape up or this U shape down. Okay? This U shape up is called concave up. Concave up. Lovely handwriting. And this U shape down is called concave down. Writing with the mouse is quite challenging. Let me summarize with the little table I made here what's going on. So let's say I have up here is the sign of the first derivative. So the first derivative is positive or the first derivative is negative. Over here I have the sign of the second derivative. The second derivative is positive, second derivative negative. So if the first derivative is positive, then the function's increasing. So here we see two different versions of increasing functions. If the second derivative were negative, then we see two different versions of decreasing functions. And then the second derivative is telling if it's concave up or concave down. So this would be a function where the first and second derivative are both positive. It's increasing in concave up. So it's a positive slope and it's becoming more positive. Here it's a positive slope but becoming less positive because it's concave down. The second derivative is negative. Likewise over here, if the first derivative is negative, the function is decreasing. But if the second derivative is positive, that means the slope is increasing, and so it's becoming less negative, and it looks like this. And likewise, here's a negative slope that's becoming more negative because the first and the second derivative are both negative. And so you can sort of piece together these curves to get a good sense of what a graph is going to look like with these sort of pieces like this. Let me show you an example I did graphically using Desmos. Let me bring up these pictures I made here. So what I have here is I have a function. This is actually x cubed minus 4x in case you care. And here I have its first derivative, and here I have its second derivative. So this is a cubic. It's third degree polynomial. Its derivative is a second degree polynomial, a quadratic. And its second derivative goes down to a first degree polynomial. It's linear, it's a line. So here's this graph, and here's its derivative. So let's look here. When this is increasing, so it's going up, 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 this needs to be positive. And we see that here. This is increasing all the way to, I'm not sure what that value is right there, but it's increasing all the way to there, and the first derivative is positive. And then this is decreasing, and then increasing. And so we see the first derivative is positive, and then it's negative, and then it's positive. We see the same relationship between this function and this one, because this is the derivative of that. This is the second derivative, this is the first derivative. So this is decreasing, and then it's increasing. And so we see negative, and then we see positive. The new thing here is the relationship between the function and its second derivative. So here we see the second derivative. So the second derivative is negative all the way up to 0. And so we should see that this function is concave down all the way to 0. And that's what we see here. It's concave down. It's got that U shape down all the way to 0. And then the second derivative becomes positive after x equals 0. And we see that it changes here to concave up. This point where it changes concavity from concave down to concave up is called a point of inflection of the graph. That's a term we're going to use a lot in the days to come. So this is an example of how the second derivative and the first derivative and the original function all relate and talk to one another. Let me do a really helpful example. It's kind of a long one, but it's a good one. Okay, let's look at this one. Determine the intervals on which f of x equals 1 over 1 plus x squared is increasing and decreasing, and on which it is concave up or down. Excuse me. So in order to do this, I need to take the first derivative, and I need to take the second derivative. So let's start with that, because increasing, decreasing is going to come first derivative, concave up, down is going to come from the second derivative. So let's do the first derivative first. So let me bring open math type here. So this looks like it requires the quotient rule, but actually I'm going to rewrite this as 1 plus x squared to the minus 1. To the minus 1, there we go. And now when I take the derivative, I just have to use the chain rule. This is like a u to this minus 1. So I have f prime of x. So this is u to the minus 1, so I take the derivative, and I get minus 1 my u to the minus 2. And then I multiply by the derivative of the inside. The derivative of the inside is just 2x. And if I simplify this, I'm going to put that minus 1 on the fraction bar itself, minus, and then I'm going to have 2x on the top of the fraction, and then 1 plus x squared on the bottom of the fraction. So there's my first derivative. I can make a copy of this. So I have my first derivative. Now let's get the second derivative. Second derivative is harder because it is going to require the quotient rule. So let me bring up math type again. So here's my first derivative. So now I'm going to do the second derivative. So the minus on the fraction bar is just going to sit there. And I'm going to use the quotient rule to take the derivative of this. The derivative of the top is 2. Then I recopy the bottom. Minus for the quotient rule. Then I take the derivative of the bottom, and this requires the chain rule. It's 2, 1 plus x squared to the first times 2x. And then I multiply by the top, another 2x. And then I have to square the bottom to complete the quotient rule. So I get that to the 4th power. Now, since I'm going to work with this, since this is not just a practicing and taking a derivative problem, since I'm going to work with this, I'm going to need to simplify this. Otherwise, it's going to be hopeless to try to straighten this out and work with this. I'm going to leave the bottom alone. I have this minus on the fraction bar, which I'm going to leave there. So let me see, what do I have? My trick here is I'm going to factor 1 plus x squared. You see I have two terms on the top, 1, 2. I'm going to factor 1 plus x squared out. And then what I'm left from the first term is 2 times 1 plus x squared to the first power, after I take 1 plus x squared out. And the second term I have minus 2 times 2x times 2x, so that's minus 8x squared. And it's still over this on the bottom, but now I can reduce this fraction. I have this common factor of 1 plus x squared, 1 plus x squared. So my fraction, my minus on the fraction bar, this divides this away, and I end up with, stop that. I end up with 1 plus x squared to the third on the bottom. And at the top, this is 2 plus 2x squared minus 8x squared, so that's 2 minus 6x squared. And so there's my simplified second derivative. Bit of a mess. Now let's go back to answering the question. Determine the intervals on which f of x equals 1 over 1 plus x squared is increasing or decreasing, and on which it's concave up or concave down. So what you're going to have to do is you're going to have to make sign diagrams. You have to make a number line that tells you where this is positive or negative. And the first step to this is to figure out where the thing equals 0, because that's the only place it can change sign. However, there's a fabulous shortcut for this on this particular problem, which you should definitely take advantage of. I'm going to zoom in a little bit here. Here's the first derivative. I want to know where this is positive and negative. And the thing that makes you have to realize that makes your life a lot easier is this right here is always positive. POS, positive. That's always positive. And if you just want to know where this derivative is positive or negative, since the bottom of the fraction is always positive, for the purposes of figuring out when it's positive or negative, you can simply ignore it. Its bottom's always positive, so all that matters is the sign of the top, and that's very straightforward now. If I make my number line here, this is supposed to be a line. I'm going to try one more time, but I'm not going to worry about it after this. Here's my number line. This equals 0 when x is 0. So when x is 0, it's 0. Don't forget about the minus on the fraction bar here. So minus 2x, that means it's going to be negative. When x is negative, it's going to be positive. And when x is positive, it's going to be negative. If I put a negative value in here, I get positive numbers. If I put a positive number into this, I get negative. So this enables me to answer the question. So it is increasing when x is less than 0, and it's decreasing when x is greater than 0. So that's the answer to the first part. So I'll answer my first part by saying f of x is increasing if x is less than 0, decreasing if x is greater than 0. Now we're going to do the same thing for the second derivative. And again, we're helped by that the bottom again is always positive. 1 plus x squared is always a positive number. So again, this is positive here. So when I'm determining whether the entire fraction is positive or negative, I may disregard this. If I want to know the exact value of the second derivative, of course I have to take it into account. But if I just want to know if it's positive or negative, well, this is always positive. So I'm not going to worry about it. So this is a little bit trickier. I've got minus this mess. So I want to know whether minus this is when minus this is positive or negative. So when is, I'm going to type for f double prime, when is minus 2 minus 6x squared, oops, sorry, positive or negative? So the first thing I want to know is when is it equal to 0. So if I set this equal to 0, let me bring open another math typing window. So if I get minus 2 minus 6x squared equal to 0, that's what I'm going to use to make my sign diagram. So we know where this is positive or negative. First I have to know where it's 0, and that divides my number line into pieces. So if I distribute that minus, I get 6x squared. Hold on, let me make this equal to 0. If I distribute the minus, I get 6x squared minus 2 equals 0. And that means 6x squared equals 2, or x squared equals a third. So that means x is equal to 0. And don't forget, if x squared equals some number, you're going to get a plus or minus. So x is plus or minus the square root of 1/3. So those are the two places where the second derivative is 0. So that enables me to make my sign diagram. So I make my sign diagram. I'll do the inking again. I make my sign diagram. There's my pretty poor number line. I know it equals 0 at the square root of 1/3. I don't need to know exactly where that is on the number line. Excuse me. I also know it equals 0 again at minus the square root of 1/3. So I just need to know, now I need to pick a test value. Test value out here less than negative 1/3, a test value in here where it's between these two values, and a test value in here where it's greater than root 1/3. And remember, I'm still going to ignore the bottom here. The bottom's always positive. I don't care about the exact value of the second derivative. All I care if it's positive or negative. Since the bottom is always positive in this case, I may disregard it. So I need to pick a number out here. I'll choose, I don't know, -1. That's less than negative 1/3. If I put -1 into here, I get 2 minus 6. So that's a negative, but there's a minus in front. So this is positive, plus. Here I can put 0. 0 is in this interval. Can't quite see those roots there. There we go. If I put 0 into here, I get -2. Because there's a 0 there. So it's negative. And if I put 1 into here, I get 2 minus 6 again, but then there's a minus in front, so it gets plus. So this enables me to answer the last part, which is it's concave up out here, and it's concave down here in the middle. So f of x is concave up on minus infinity to minus square root of 1/3. Terrible notation. I wish I had my paper, but I don't have my document camera. Or square root of 1/3 to infinity. And it's concave down between those roots. That's a very long, complicated example. It gets across. It's a good practice problem for understanding. You'll have to do problems like this. So this is a very helpful example I've gone through carefully to help you see sort of the steps where you take the derivative and you have to do simplifications And then you have to make sign diagrams and tricks like looking at things that are always positive so you can ignore those factors. One last comment and I'll be done. That's involving a particular application. And I'm not going to go into a lot of detail on this right now, but if you have something whose position is given by some function p of t, we've already talked about that if you take the first derivative, if you take the derivative of position, you're going to get velocity. If this is in centimeters, then velocity is centimeters per second. It's how fast it's moving. The second derivative, the rate of change of acceleration, the rate of change of velocity is acceleration. So if you take the second derivative of position, you get acceleration. And there's lots of applied problems around this. It's one of the most useful things you can use in a physics class is this position, velocity, acceleration relationship with the derivatives. And that is all.